We will now solve problems from deflection of beam chapter, which is chapter 4. Those problems which have come in GATE, mechanical engineering. So the first question in this chapter in the booklet is two identical cantilever beams are supported as shown with their free ends in a contact through a rigid roller. Yeah, that's a good question. So we have two cantilever beams, one here and one here. So they are identical cantilever beams, which means their length, Young's modulus, and the moment of inertia all are equal. There is a force P. Now the free ends of the two cantilevers. So free ends are, let's say this is A and this is B. So at the free ends, what is going to happen? So option A says that equal deflections but not equal slopes. And option B is equal slopes but not equal deflection. Option C is equal slopes as well as equal deflection, and option D is neither equal slopes nor equal deflections. So let's see what is going to happen. So this is a rigid rigid roller, which means that it cannot deform. So when the force is applied, A and B will be in contact through the rigid roller, which means that they will be deflecting by equal amounts. So the deflection has to be equal. So now we rule out the options. So option A says equal deflection but not equal slopes. So that is a probable answer. Option B says equal slopes but not equal deflections. So that is wrong. So A is possible. We don't know. It is possible that it is the right answer. B is obviously wrong. C says equal slopes as well as equal deflection. Let's see what happens. It may also be correct. And option D says neither equal slopes nor equal deflection. So that is also wrong. Equal deflection is absolutely there. Now let's see what happens to the slopes. See, in this case, A and B are not rigidly fixed. They are just having the support. So now what happens is the slope will not be equal because A and B are free to rotate. The sections are free to rotate as they want. Hence the right option is option A, which is equal deflection but not equal slope, and option C is not correct. Let's see what is question number 2. The question 2 is like this. It's basically like two questions linked. So I just draw the figure first for question 2 and 3. These are the linked questions. A steel beam of breadth 120 millimeter and height 750 millimeter is loaded as shown in the figure. So we have a beam which has width of, or the breadth of 120 and height of 750 millimeter. Its span is 15 meter, and there is a UDL, uniformly distributed load, of 120 kilonewton per meter. This is 120. This is the value of Q, let's say. Now, what is the question number 1? And okay, one more thing. This is made of steel for which the Young's modulus is 200 GPa, gigapascals. Now, what is the first question? Question number 2. The question number 2 is the beam is subjected to a maximum bending moment of. So, what is the maximum bending moment here? In this case, this is a UDL. So, maximum bending moment is QL square by 8. That is the maximum bending moment. So if we just solve this problem, we get Q is 120 kilonewton per meter multiplied by length square is 15 square by 8. This is nothing but 15 into 15 square, which is 15 cube. The value is 3375. kilonewton meter. That's the answer. So option A is 3375, option B is 4750, option C is 6750, and option D is 8750. So this is the right answer. Now what is question number 3? That's linked to question number 2. The value of maximum deflection of the beam is, okay, now we can, of course, in the examination hall we can solve the problem and get a maximum, but it is better to remember the deflection. Maximum deflection delta is 5 upon 384. I'll just cut it and write it once more. 5 upon 384 W L to power 4 upon EI. That's the value of maximum deflection, which is at the center. So if you put the value of the quantities here, W is nothing but Q, which is 120, L is 15, E is 200 GPa, and I is 1 upon 12 into width into height, and all that calculation if you do, you will get the deflection is 93.9 millimeter. So let's see the answers. Option A is 93.75, B is 83.75, C is 73.75, D is 63.75. So 93.9 is close to 93.75. That's the answer. So please, it's a request to remember important deflections and bending moment formulae. Like for this case, UDL on a simply supported beam or UDL on a cantilever beam. These formulas should be remembered so that you can apply them directly without wasting time on figuring out what the numbers will be. So let's move to question number 4. Question number 4 is the second moment of a circular area about the diameter D is given by. This is a straightforward question. This is the circular cross section and this is the diameter, and the diameter value is D. So obviously we know this is the moment of inertia is pi by 64 into D to power 4. That's the answer. So it is option D. So option A is pi by 4 D to power 4. Option B is pi by 16 D to power 4. Option C is pi by 32 D to power 4. And option D is pi by 64 D to power 4. So this is the right answer, option D. Now the fifth question. The fifth question is like this. A simply supported laterally loaded beam was found to deflect more than a specified value. Simply supported and laterally loaded, which is like, if I draw a very simplistic figure, this is a simply supported beam and laterally loaded by some force P. It was found to deflect like this. The deflection was more than the specified value. So the deflection required would have been probably here, while it deflected more than that. So this extra deflection is coming, delta extra. So which of the following measures will reduce the deflection is what we are supposed to figure out. Now the measures are: A, increase the area moment of inertia. Absolutely, that will decrease because delta is proportional to P and L upon EI. It is directly proportional to the load, which means if you increase the force, it will increase the deflection. If you increase span, it will increase the deflection. If you increase E, it will decrease the deflection. And if you increase I, it will decrease the deflection. Now we have to decrease the deflection, so we have to either increase E or increase I or decrease P or decrease L. Let's see which of the options are given. Increase the moment of inertia, absolutely. That is the one which will do it. So let's see if anything else also there. Option B says increase the span of the beam. Wrong, because it will increase the deflection further. Select a different material having lesser modulus of elasticity. That is also wrong. Decreasing the modulus of elasticity will increase the deflection. And option D is magnitude of the load to be increased. That's also wrong because it will also increase the deflection. So all the things are wrong except option A, which is increase the moment of inertia. Now what is question 6? Question 6 is like this. The area moment of inertia of a square of size 1 unit about its diagonal. So, okay, that's a good question. Question number 6. So, we have a square of side 1 unit. This is 1, 1, 1, 1. But we are not supposed to find out the moment of inertia about its centroid side. We have to find out the moment of inertia about the diagonal. So how do we do that? So we know that the moment of inertia I about the axis passing through the centroid and parallel to the sides. This is, let's say, side 1 and side 2. So I1 is 1 upon 12 into side cube into side. So it is b into h cube, which is 1 and both 1. So it will be 1 to power 4 or 1 upon 12. Similarly, I2 is also 1 upon 12 into 1 to power 4, which is 1 upon 12. Now we have to transform the moment of inertia to the side, to the diagonal. The angle between the central the central axis and the diagonal axis is 45 degree. So what happens is the transformation is I about the diagonal is equal to I1 into cos square 45 degree plus I2 into sine square 45 degree. That's transformation. So if I do this, I get I1 is 1 upon 12 into cos 45 is 1 upon square root 2. So square is 1 upon 2 plus 1 upon 12 into again 1 upon 2. So that is 1 upon 12. So the answer is 1 upon 12. Now let's see the answers which have been provided. The options: A 1 upon 3, B 1 upon 4, C 1 upon 12, and D 1 upon 6. Answer C is the right one, which is 1 upon 12. Now let's see question number 7. Question 7 is a lean elastic beam of given flexural rigidity EI is loaded by a single force F as shown in the figure. Okay, so this is the elastic beam. Now there is a support. It's like a overhanging propped cantilever, and there is a force here acting on the free end, which is F. How many boundary conditions are necessary to determine the deflected center line of the beam? Now that's a good question. See, we know that the deflection equation is given by d square y upon dx square is equal to m upon ei. Now here, because the force is fixed, and which means that the value of force is fixed as well as the location is fixed, so that for a particular location of the beam which is at the distance x from the center, it will fix the moment also. And we also know that the ei value is constant, which is the flexural rigidity is a given quantity. So that means m upon ei for a given section of the beam will be constant. So now I know how I can integrate this equation once. It gets me dy by dx is equal to integration of m upon ei plus c1. One more integration will give me double integration of m upon ei. This is dx actually, plus integration of c1 dx plus c2. So to solve the, to get the value of y, we need to have c1 and c2. So two values are required. So two boundary conditions are required to get the equation of the deflected center line. Now let's see the options which are provided. Option A is 5. Option B is 4. Sorry, the first option is 5. The option B is 4. Option C is 3. And option D is 2. So the answer is 2, which is option D. So that is all in this chapter, and this is also a good and important chapter because it's also used heavily in the design of various structures. So again, and most of the times your bending moment and shear force diagrams, the bending stress and the deflections will be clubbed in one question itself. So this may not occur as a separate question on its own, but it may be part of a question in which you have to figure out a bending moment and figure out bending stress or shear stress and figure out the deflection.